Welcome to the Building Energy Management session here at ARC. My name is Rick Riss. I'm an analyst at ARC. I cover areas such as, I will be covering more in the future of smart cities and microgrids. I have a background in control systems for chemical, oil, gas, operator training. I also will run the drone session here coming up at 4 o'clock and another operator training simulator session on Thursday. So I have some particular interest in the building energy session, as I recently designed and built my own house to the German passive house standard. So it is 100% electric, no oil, no gas. It's a super efficient house. It's at net zero plus 30% export at the moment, which will eventually be an electric car as I connect, all right? And it's an off-grid inverter, so I have the possibility, when I can afford the batteries, which are still a little expensive, to basically have my own microgrid. So let me first introduce our speakers. We'll basically go from top to bottom. We have only 2 speakers today and 2 panelists. We'll start out with Dr. Rahul Mangharam, who is a professor at the University of Pennsylvania, and he will be talking about, I think he has a lot of stuff really associated with demand response and microgrids. Our second speaker is Albert Gilowitz, who is the Director of Energy and Utilities at Purdue University, managing the facilities for that whole university. So, he will really be speaking about the asset management and the big picture, electric, heat, and management, a whole campus worth of buildings. We have some expert panelists as well. We have Russ Agrusa, who's the founding president and CEO at Iconics and an active member in the OPC Foundation. And also we have a panelist, Chris Evanich, I hope I got that right, who is the manager of microgrids at S&C Corporation, a leading supplier of microgrid components, hardware, software, engineering, system integrator. So I'm going to make a brief introduction, and each of the speakers will be probably speaking for in the range of about 25 minutes. It's very interesting to note that of all the new electric power, which is the upper box there, that went on the grid recently, about 60% of all the electric power that went on the grid in the US was solar and wind. About 30% of new generation is natural gas. This kind of a graph really gives the really big picture, but it shows where all of that energy is going. But basically, you're seeing an awful lot of disruption going on recently. Instead of, central station power, you're seeing, first of all, a movement from coal and oil and gas will eventually move to even more renewables. So we can expect that this picture will show up quite differently. It kind of makes solar, wind, and hydro look kind of small, because solar, wind, and hydro actually don't reject energy as heat. Obviously when you have a coal or nuke plant, a substantial amount of the heat energy that came out of the fuel reaction is rejected as heat, which is always a good possibility for combined heat and power if you need to heat buildings, all right? It's pretty interesting to see that. And I think if you heard Jason Hanley's presentation from Duke Energy today, and you'll probably hear it in a number of other places, but really the electric grid is in a very disruptive transition. Their business models are changing. Where they used to be central station power, coal plants and nuclear plants are shutting down. That's mostly driven by cheaper natural gas, but it's also driven by solar and wind, and it's also driven very much so by conservation and flat increasing demand of power. People are putting more efficient lightings, LED light, they have more efficient heating systems. House construction standards are much better, so the amount of energy that was inherently needed by a building was less to start with. That was actually my strategy. Use less to start with, you don't need so much energy to heat or light. One of the key things I think about smart grids or electric grids is really about the metering of the energy. When you start thinking about how you automate some of those things, some of the key points are metering the energy. And so I happen to just draw that smart meter there on the control system side on the right. That's a very interesting thing. You know, obviously the utilities started to coming out with smart meters, primarily for billing purposes, and they kind of thought those were my meters. They are helping me, all right? But with AMI, advanced metering infrastructure, really it's a lot of end users. The consumer himself wants to know what that meter is saying. There's a lot of data in that meter that a lot of people want to get to. You know, Google and Amazon want to see how your electric consumption goes throughout the day. They really want that data. You know, you probably don't want to give it to them, and the utility is actually probably obligated not to give it to them. But there's a lot of data that you could use as a consumer to help improve how your utilities, you know, when did your hot water heater kick in? When did your heat pump kick in? What's going on in your building? And also, the utility companies like Duke Energy, they would like to control the loads in your house. You know, I mean, one option for non-dispatchable renewables is to put batteries on the grid to help alleviate or compensate for the lack of spinning reserves with coal plants and nuke plants shutting down. So batteries, you know, batteries and inverters can respond very, very fast. Actually, supercapacitors can respond super fast to frequency control of the grid, which is the main control of power on the grid, is done by frequency. So in any event, utilities like Duke Energy desperately want, not desperately, but certainly foresee in the future that they want to control your hot water heater. They want to control your heat pump. They want to be right at the breaker box telling you when they can use. And the advantage for them to do that is with demand response, they can shave peak loads off. If they can shave peak loads off in the hot summer days, you know, just for a few hours in that day, they can avoid the construction of new peaking power plants, and that can therefore reduce cost. And it also reduces load on transmission lines. So a lot of changes basically going on. So the trends for building energy is, you know, very fundamental for building energy is the design of the building. Design that building to be well insulated, to have the appropriate solar gain, to have the appropriate ventilation. Obviously, you're concerned with the appropriate comfort, you know, comfort level for the occupants, that which is temperature and humidity zone. And of course, you have to have fresh air. If you make a house too tight, you would get into carbon dioxide problems. You have to worry about things like radon and other things. But so the design is really critically important. You know, a lot of times here at ARC, we're focusing in the automation and the operation of those assets. But design is particularly critical in the area of buildings, because if you've got a building that has no windows in it and you're trying to heat it, I don't care what kind of control system you have, it's just going to burn fuel. You know, they just can't optimize an inherently bad design. So, but nevertheless, there's tremendous amount of possibilities and energy savings, as several of our panelists are quite well aware, that you can operate those assets and save a considerable amount of energy. So there's building standards. There's obviously increased attention to the inherent energy content of the construction components of buildings, like concrete is a very energy intensive building material, but pretty critical one at times. So the electric grids are obviously moving from central station power to DER model of physical construction on the electric grid. Technology obviously had a lot of gains in the efficiency of wind turbines and the cost of wind turbines. The technology has improved. There's many, many generations of wind turbine designs that have come out. And also solar panels are cheaper to buy and cheaper to install and have somewhat higher efficiency, still in the range of 20%. Demand response is kind of an untapped potential. It is a huge advantage to a utility if they can synchronize all of the users in any particular area, town, or university. You know, smart city, obviously there's a great deal of emphasis. Many modern cities have got a real communication network where they have building, administrators within the town, the utility, and the homeowners all kind of cooperating to make a more efficient general flow of all kinds of things, from traffic to power to utilities to waste treatment to trash removal and things like this. the growth potential with sensors, wireless, gateways, edge devices, data analytics is still really, really huge. There's so much potential to save energy in building energy management. And of course, we always have the problem of cybersecurity. A lot of times, the cybersecurity problem is more about controlling the customer data. It's not just about people hacking into the grid and shutting down resources. Utilities are very, very concerned about protecting their customers' data. So with that, I'm going to turn the presentation over to Raul, and